Okay, now let's practice the Newton's second law in the momentum form on this problem. So this is example number 28 on page 282. A 1300 kilogram cannon is used to fire a 72 kilogram cannonball horizontally, as you can see it on the picture. The cannonball travels at a speed of 55 meters per second relative to cannon. So that's something that we need to be careful. It's not relative to ground. Okay, so it looks like we also have relative velocity problem here. Find the velocity of the cannon relative to the ground, assuming the cannon rolls freely. So we can see that cannon is much heavier than the ball, right? Cannonball. So if the cannonball relative to the cannon is moving at 55 meters per second, approximately it's relative to ground should be the same, right? Not exactly, but it's going to be similar because the cannon is so heavy, it's not going to move much compared to the cannon's speed. So we can kind of think about the estimations that way. Okay, so we are trying to find the velocity of the cannon relative to ground. And again, we're assuming there's no friction and also no drag, and so that the rollers are free to roll. Okay, and we will draw free body diagram because again we're dealing with the second law. You will use conservation of linear momentum. We really will start from Newton's second law in momentum form, and it's going to lead us to the conservation of linear momentum. So when we say apply conservation of linear momentum, we are not really saying anything different than using second law in the momentum form. Okay, so it's really nothing different. You just need to understand the process to be able to do this algebra. So the estimation, again, if you think about order of magnitudes, instead of saying like 0.11 or 10 meters per second, I would definitely say 1 meters per second, or I can say it's much less than 55 because that's a velocity magnitude given in the problem compared to that, right? We can make that estimation. So again, the key step is we take cannon and the ball as our system. And you can see that here in the bubble, kind of, this is our system. The dashed one on here is the initial case. And here we have the final case, or sometime later after it was launched. These are the cannonballs, okay? And let's think about the free body diagram first. So we have our coordinate system as we need it. And then we will have normal force coming from those rollers from the ground, so that's represented by N, and the total weight force, because we are looking for the entire system, we're just going to have one weight force, right? And that has to be for the center of mass. Okay, so the center of mass point here is really given for some time later, so when the ball is probably right there. So it's still closer to the cannon, not the ball, because ball is much less weight. But again, it's not gonna be in the middle of cannon either, because there's also a piece of the system, which is the ball. Now it's much far away from the cannon, so it's gonna be somewhere in between them. Okay, so again, we ignore the force exerted by the explosion, because that is an internal force, right? Yes, remember the plunge problem, the carts, there was a plunge, and then we push the pin, and the plunge was released, and that force was internal force, right? Just like that, this explosion is going to be also internal force. It happens within the system. And okay, and the forces on the free body diagram only act on the y direction. There are no x components. But since the ball is traveling horizontally along the x direction, let's investigate the linear momentum along the x direction. Okay, and what we do first, we start with the equation. Since this is not for a particle, we are using capital P as the momentum in the equation. That's the linear momentum along the x direction is px. And again, it has to be consistent, so also the forces along the x direction should be considered here. And looking at our free body diagram, there's no forces along the x direction, so that becomes 0. Then dpx over dt is 0. Again, this is the conservation of momentum, okay? You don't need to memorize anything. You just start with the second law in the momentum form, and that's the boxed equation here. And then think about draw your free body diagram, think about it, what you have along this direction, and then again, we don't have any net forces along x, so we just crossed it out. That tells us the rate of change in p, x is 0. So there's no change in px. Or another way of saying that, it is constant. What does constant mean? If you look at the right before explosion and right after explosion, so this is the initial case and this is the final, right before and right after, they are going to be equal to each other, okay, because it's not changing. So that is what the conservation of momentum is. Then, remember, these are capital P, that's because there's more than one pieces in the system. And now we are going to kind of split up into pieces. We have cannon and the ball. So we're going to use C for the cannon and B for the ball. And each term will be split up into 2. Okay, and we can see it in here. Initial momentum has 2 pieces now. One for the ball, one for the cannon. And final should also be considered as the same amount, 2 pieces. So there are 2 terms in there. If you look at the labeling, again, x is for the direction of the motion, or the momentum in this case, and I is the initial, F is the final, and C and B are cannon and the ball, respectively. Next step is writing those momentum terms in their definition. We know that P is mv, right? Mass times velocity. So we're going to be careful with the labeling. We need to be consistent. So for example, P, the first term, pxic, is for the cannon, right? So you're going to use the mass of the cannon and the velocity of the cannon, initial case along the x direction only. And you're going to add that to the second term here. So since this is B, that's the mass of the ball and the velocity of the ball initially along the x direction. And you can complete the rest of the equation that way. Just write the equation. Don't focus on what you're going to plug it in, okay? Just keep working on the symbolic equations first. After you get this, now we're going to think about what do we know about this. We know that initially the ball and the cannon are at rest. So that means this velocity of the cannon initially is 0. It was at rest, so it doesn't even have any components, so x component will be 0 as well, and so is ball, right? And left hand side goes to 0. Then right hand side we have 2 terms, and since the initial momentum in the x direction was 0, that's why we're getting this. So we're not given the ball's velocity relative to ground. If you remember, let's go back to figure, actually the statement in the first figure. This 55 meters per second was relative to cannon. So what we have in this equation is the cannon velocity, but this is relative to ground. Unless it is specifically said it was relative to something else, then we would know. But these equations they assume they are relative to ground. So if it is something relative to something else, then you have to stop there and then think about, make a plan again, use the relative velocity equations and such. And this is also the velocity of the ball relative to ground, okay? And if you look at what we are finding is that's, again, it's the velocity of the cannon relative to ground, but we are given the velocity of the ball relative to cannon. So we just need this to be relative to the ground, okay? That's going to be the next step. So let's apply relative velocity equations. If you remember, we choose 3 things, right? We have the ball, we have the ground, and we have the cannon. We have 3 things. So the velocity of the ball relative to ground is, you can write it using those 3 letters. It's from chapter 4. B starts with B, so you have B first. I'm gonna focus on this equation here. So remember, the first term comes first, and then last term, the last letter G comes at the end, right? In between comes the third letter you haven't used yet. So you kind of sandwich it. And these are bolded V's, that means these are vectors. So this is a vector equation, okay? So considering that, let's see what we have on the right side. VBC is the velocity of the ball relative to cannon, and that's what we are given, right, in the problem. And VCG is the velocity of the cannon relative to ground. That is exactly what VXFC is, because that's what we're trying to find. So this is going to turn into then the velocity of the ball relative to ground is ours from the earlier equation here. This is what we have. This velocity of the ball relative to ground, and that's going to be equal to the velocity of the ball relative to cannon plus velocity of the cannon relative to ground, and we are also replacing this with that. So this is the equation we're getting. Okay, I hope this is clear. It's just like kind of, we already have stuff given in the problem. We are just substituting with what we have in this relative velocity equation. And this is what we're going to plug it into that equation we got from the second law right up here. Okay, so again, this is this equation here. 0 equals to MC VXFC, right? Plus we got what the velocity of the ball for the final case along the x direction is. So we just are substituting this term here, and that's the mass of the ball. Okay, so what we've done is we had two unknowns, now we have the same unknown. So using the velocity, the relative velocity equation, we reduce our unknowns into one because we got another relation between those two unknowns, and we combine them, one from the second law, the other from the relative velocity. This is the equation that we get, and now we can solve for VXFC. Again, you can do some algebra here. I'll probably do distribute this into both first, and then try to separate VXFC, so it will have the coefficients of MC and also MB. You can put them together, and on the other side you will have MB times 55 meters per second. But if you're putting that on the left side and then swapping the sides, that will be negative here, as we show. So you can solve for VXFC. First of all, it's going to be negative, and it is very small, 2.9 meters per second. Again, we just need to plug in the mass values, but it's already given in the problem to get this answer. Okay, and let's box this answer. It is negative, doesn't make sense, because the ball is going to the right side, positive direction, right? The cannon is going to recoil the other way, and it's going to be along the negative direction. And that makes sense, so that the center of mass point doesn't change. It still stays the same, right? So if we go to the bottom as a discussion, our answers are in good agreement with our estimate, and the answer come out negative as expected because it moves to the left. We choose our Furbat diagram in such a way to hide the explosion force. In reality, there would be friction to slow the cannon, otherwise it would move forever to the left. So we are again making it simplified by ignoring some of the present forces. But also the wheels might be blocked or locked, so if we consider the entire system's center of mass and apply Newton's law, we find sum of Fx equals to ma, center of mass x, and sum of Fx goes to 0. That means the acceleration of the center of mass along the x direction is 0. That means the velocity of the center of mass along the x direction is constant. And since the center of mass has 0 velocity initially, it will stay at 0. That's why it doesn't move. The center of mass point doesn't move. And but as you can see, the pieces in the system will move to make sure that center of mass point does not move.